Okay, that's fine. And what I'll do is I'll share my screen. I can find share. There we go. Good. Hello. That's a young student ready to learn some crypto, I think. Great. I don't think you can start learning cryptography too early, so good for you. As long as she's not helping in the exam, then you're okay. Right. Okay. So we'll make a start. Does anybody have anything really that they want covered in this session, or will I just go over the material from last week and then the coursework again?
Hi, Bill. Can you hear me at all?
Yeah, perfectly.
Oh, hi. Yes, hi. It's Steve here. And good evening or good morning or whatever to everybody else as well. Just got a quick question about the homomorphic encryption slide that's in the PDF or the PowerPoint for this week or last week. As you know, my topic for the coursework is homomorphic. So on one of the slides, you've very helpfully sort of outlined, if you like, the sort of expression that underlies the homomorphic encryption, which is C equals P times Q plus 2 times R plus M, and some other things. And I'm just wondering if it's possible to just kind of outline what the different parameters are there, or is that maybe too heavyweight for an evening like this?
No. Well,
I'll put you on the spot. I'm sorry.
People can switch off, but please don't turn off. But you can switch off now. So this is it's a great topic, and just let me try and find where my little demo is. So I think I've got it. I've got the demo here somewhere. So I've implemented it in Python. It looks really complicated, but actually it isn't too bad when you actually look at the actual code itself. So as you correctly, that's not that one, as you correctly say, it's this method here, DGHV.
Just as an interjection, where do you find the time to write all this stuff? It's a huge amount of background material there. I'm sure this is a wonder to everybody then, Bill.
Yeah, well, I mean, I think it's we wouldn't want to teach anything that we didn't know ourselves. It's such an interesting area too, and it's nice to be at the cutting edge. We like to kind of simplify things, so we'll take a really complicated research paper and maybe try to distill it down and to make it much simpler. I don't think there's enough content on the internet that really tries to take the level down a little bit and explain some of the core concepts.
I would definitely agree with that. Having read lots of, well, not lots, but several of the papers, it's like trying to sort of wade through sort of spaghetti letters in many cases.
So it was Gentry's method that you're defining, and it's full homomorphic encryption. So most of the other methods use partial homomorphic, where you can multiply pair layer, for example, and you can take a square, but you can't do things like add and subtraction and so on. So Gentry was the first method to actually implement a full homomorphic encryption technique, and I think it's implemented in quite a few Python libraries, and I'm fairly sure it's certainly in the IBM libraries and within Microsoft. So the core of it is this, where you take your integer values for your data and then make it into ones and zeros. So you go right down to that level. So in this case, you create a cipher value. So the cipher value is a very long integer value that represents each bit. We take a random number P there, and we take two other random numbers Q and R, and a single bit M, and then we calculate it like this. P is the secret key, so we keep that back, and it's impossible to know what the value of the bit is because we've used 3 random numbers there. When we want to decipher, we take the cipher value that we've created for the bits, we do some operations on it, and we take the mod of the P, our random number that we've got for a private number, we take a mod P, and we get our bit back again. And amazingly, it does work. This is my little simple adder, so it just adds 2 binary numbers together in a homomorphic way. So every single time you should be able to change your bits, and you can't tell from the cipher bits if it's a 1 or a 0. So as a result here, we can see there's the result that I get. If I add that plus that, I get that and that. I've got a carryover this time. If you want to see what an adder looks like, 2-bit adder circuit, you take it right down to the circuit level, so every function that you have now becomes like a whole lot of exclusive OR and AND gates. So the Python code isn't too long, so if you wanted to implement that code there, I've used very small random numbers because it doesn't take long before it possibly overflows Python. But you should find that this should work from there, and it was based on this original paper in 2010. Does that help?
It does, thank you. That's very useful. I've been looking at Microsoft Seal, which implements some other aspects of that as well, but
yeah,
not as clearly.
Yeah, no, I think they'll obviously implement a lot of the libraries that would be involved. So it's I've got just a few things like whether Bob is older than Alice and so on.
Hey, Bill.
Okay,
that's very useful. Thanks so much.
Okay, thank you.
Yeah, thank you.
Sorry, I was going to say, how many bits of the plain text do you think this method would be able to handle before an overflow in the ciphertext?
Well, that's something for you to find out, I suppose,
Okay.
if you're taking that as a subject. Yeah, there's a Python thing in there, because we're not using this mod of a prime number. Then the numbers become very large, and I think Python breaks after a certain amount. So that might be something you could investigate, whether you can break that homomorphic encryption. Certainly, when I've done the tests, to randomly encrypt, just say 1 bit, a 0, you get an even number, you get an even split between odd and even cipher values produced. So it's impossible to determine the actual bit that you've encrypted. But obviously that would depend on the random number generator that you're using, and many of the random number generators are weak. I think this one here is taking its randomization from the operating system. It certainly does that in Linux, but obviously if you spotted that you had a slightly more chance to be biased towards one bit or the other, then that would make the cipher weak. But I can't remember where it breaks, but you might want to just keep ramping these values up and seeing where you get.
Yeah, so I didn't mean necessarily for ramping the random values up. I just meant ramping up the plain text bits. Or am I misunderstanding? So bit A0, instead of just having more than just A0, having bits A through A5, if you want to get the 32.
Yeah, you can have an infinite number of bits, but obviously you've got to create each bit as a single cipher value, so it's infinitely scalable, and it's just like an electronic circuit. You can have an infinitely large number of bits coming in and an infinite large number of bits coming out. So it's not limited to 32 bits or 64 like a processor has to deal with. So it's quite efficient when it's dealing with a lot of bits, as opposed to processors with 32 and 64-bit registers, which have to move the data in and out of the registers to do complex operations. This can be implemented as like a Boolean circuit, and it doesn't actually need a processor at all. But obviously, it's dealing with large numbers, so that's obviously where the processing comes in. Does that explain?
Yeah, I think so.
Good, yeah. So there's examples there, and I think they work. We certainly had a dissertation on it last year, if anybody wants to see that, and it got a distinction grade, and he implemented this type of method here. I think it was to do with CD encoding, the methods that CD-ROMs use to be able to add noise into the signal in some way. Any other questions? I know it's tough for these things, and I'm not expecting you to know the details of the maths inside out, but certainly it's good to know some basic principles around it. There's an interesting one where you can use a public key. I think I've implemented it here. Where we can generate a public key and a private key, because the method I've just shown you uses a secret key, so that's obviously quite good in terms of encrypting the values. But if you want to send someone your public key so they can encrypt for you, then I think this method here generates a long public key that you would send someone to be able to decrypt the result. Any other questions? No, I've sent you all to sleep.
No, that's very interesting. Thank you.
Okay, good. Yeah, the Microsoft Seal package is very good. I think Microsoft are all open source, so it'll be interesting to find out. Did you manage to download it yet? Have you had a chance to try it out?
I have, yes. So I've installed Visual Studio 2017. I've got the example files downloaded from the Microsoft Seal website. I've also been in touch with the Seal team as well, just to get some sort of background clarification on things.
That's Redmond, is it?
I beg your pardon?
Is it the Redmond team? Is it the team in the US or?
I think they probably are based in Redmond, but I can't be absolutely sure without looking at their email signature. I was considering them as sort of a cyber entity rather than having a physical location, but I guess they must be somewhere. So I've compiled and run the examples, and I'm starting to modify the examples as well, some of the core values, and just kind of getting into the detail of how the algorithms work. And also the other module that I'm taking, like some of our other colleagues on this call, is the incident response and malware analysis one, where we've been looking at debugging recently as well. So I'm going to see if I can get the debugger working in Visual Studio and see what's going on in the background as well.
That's a really good idea. I think if you want to look at the bottleneck that's been provided and understand where the main hit for processing time is, then it's good to get the debugger out. I think you can get some nice profiling tools to understand where the core things are. So yes, I assume it's in C++. Is that right?
It is, yes.
Yeah. So it'd be interesting to find out. So were you thinking of like implementing a few different examples of it, maybe kind of push it to its limit?
That was the idea, yes. There was a particular thread which I've communicated with you in the background via email, a particular sort of take on this just for the coursework, but it will include trying to profile the different mathematical operations as well, and seeing which ones are most efficient. So there's the adding, the taking away, the multiplying, and so forth, and combinations of those. And if I have time, I'd like to try and implement it on sort of embedded Windows on a Pi, Raspberry Pi, if that's possible. I'm not sure at the moment whether I can build the code and sort of export it for a different target, but that's something I'll look into if and only if I have the time. I want to focus on the sort of PC side of things first.
Yeah. Yeah, because I mean, I think the Raspberry Pi is an ARM architecture now rather than
Yes,
Intel.
that's
So
right.
you'd have to kind of compile that. Certainly, the Visual Studio for Mac doesn't allow C++, which is I think a weakness of it.
Okay.
But it's it'd be interesting to see if you can get it to run. But I mean, watch your time, of course, because you
Yes.
can go to infinity. This isn't
That's
a
true.
dissertation, but might be the first steps into your dissertation. So I think just make sure that you're quite efficient with the time and that you can hand it in and you've finished all the bits of it.
Sure. Okay.
Great. Okay. Anyone else with any questions? You can wake up again, and we'll. I'll just go through the presentation and I'll come back to the coursework if that's okay with everyone. So there was a bit of a glitch in the lecture this week, so you won't see the lecture because something went wrong with the recording and it kept crashing. So I apologise for not having the lecture there, but what I did is I went back and I recorded the uh, the lecture as it should have been, and you should find that the slides are there. Um, I'll give you more of a heads up on the questions that I'm going to ask around this. So there's nothing to be too scared of. It goes into a bit detail, but it's just trying to give you a heads up on some of the key areas. So the PDF is there. I think it should be in the GitHub too, and the actual lecture, the recorded is at this link here. I've got a few articles that you might want to look at in your own time. I post to Medium, so if you're looking for some thoughts around quantum robust crypto or lightweight, then have a look at the Medium posts. A lot of good stuff around there. But make sure that you spend your time looking at research papers too. So for the presentation this week, if I can get it to run, is here. So the main focus is is really for us to try and understand where the industry is just now and where it's going, and understand some of the bumps in the road and how we can rebuild systems. So some of the methods are up to the minute. Lightweight cryptography has certainly been applied. Tokenization is happening in the banks just now. Zero knowledge is a big deal in many systems. Homomorphic encryption, quantum robust encryption are moving ahead, and hopefully once the technology catches up, they'll be there. And things like ZK snarks are being implemented in Ethereum and in blockchain, and range proofs gives us a good way to preserve privacy. So for the lightweight crypto, basically the crypto that we've designed doesn't really fit for many limited devices such as embedded systems, 8-bit processors, RFID tags and sensors. Those tend to be passive tags. A passive tag is that doesn't actually have a battery, so it must power itself up from the radio wave, which is sent to the device, and it powers enough energy up and then sends something back there. So many of the methods that we have, especially in public key encryption, aren't going to run on these lightweight devices. Even things like AES with its 10 rounds and S boxes and swapping of columns and rows just aren't going to work. They're also block ciphers, so you're going to have to reserve at least 128 bits of space to be able to process the block, and so on. So we focus typically on the power drain and getting a balance between the drain and the power, and the performance of the crypto method. Doesn't do any good if we're very efficient on the battery, if it takes 10 minutes to do an encryption. So we're just trying to find a sweet spot between battery, drain, performance, and the number of gates that's actually used, along with the amount of RAM that it uses up in memory, and obviously the ROM that it needs to store the actual program. Because remember, some of the processors we use now are actually very limited. So we typically define an area that the crypto would take up, and that gives us a basic measurement. So NIST have defined a number of competitions for crypto. So there was the AES standard, where the rain dial method won. they assessed all the different methods and they had to peer review and they looked at side channel attacks and so on, and that won. And then for SHA-3, it was the same researchers again who won the SHA-3 standard hashing method, and they assessed SHA-3 for things like the gates and security, power drain, and so on. So now NIST are looking at a competition for lightweight cryptography and have a number of methods which they've actually outlined that will now go to a runoff. So there are block ciphers. They're typically 64-bit blocks. Some of them are kind of compatible with AES, but obviously are more efficient. There's a whole range of stream ciphers, and obviously RC4 and ChaCha20 are in there too. The advantage of stream cipher is it just needs an XOR gate. We take a passphrase, we generate a stream cipher, and then we just XOR the bit stream data stream with the key stream. And then on the other side, we do the same. We generate the same key stream. We take the cipher stream, and for every bit, we XOR them together. Rabbit is used quite a lot in the industry, but there's a number of ones in there. For the hashing methods, they're replacing the traditional MD5 in SHA-1 and SHA-256, but they're implementing new methods. So Spongent is there, Quark, Photon, and things like that are lightweight hashing methods. And we can have MAC methods where we share a key and we sign a hash and we can authenticate the other device. And then for public key encryption, there's not that many things around, and Ellie, I think, is the only one that's really been proposed just now. So those are some of the techniques that could be used for lightweight crypto, but the designers need to understand the strengths and weaknesses of each of these. So there's a lot of research papers you'll find that will outline some of the techniques and give you a benchmark as to how much battery strength, battery power they'll use up. So you would typically search for lightweight crypto and just find a paper that's quite up to date. Review of lightweight blocks, ciphers 2018 looks good, cited by 14 people. So that one looks a good technique, so you might want to look at something like that if you're doing the lightweight crypto. You can see there's quite a lot of surveys and things like that. Just let me try and find where that paper's gone. It should be there. And when you look at it, so that's the platforms. They'll typically assess it on an ARM platform rather than a Intel, because ARM is the almost de facto standard. There's going to be a lot more ARM processors around than there is Intel. So hopefully they're going to show us what the assessments are in there. Just keep going through the paper. It's just outlining lots. So there we go. Some results coming in there, giving us the basic specification for it, the kind of type, and then I think we saw there that there was some evaluation of the throughputs. So I can see the spec looks to be really fast when it comes to 8-bit processors, but down here we have other ones and there. Okay, so there should be lots of papers to review and lots of code and GitHubs and things like that. So the next area is quantum robust crypto, and the problem we have with quantum computers is that Shor showed that you could crack RSA, factorize the prime numbers, and you can also crack elliptic curve, along with discrete logarithms such as LGAMO. So all our existing public key methods that we use to sign things are gone when quantum computers come along. They're probably looking at a 5 to 10 year window before they can be powerful enough, but obviously quantum computers are targeting the cracking of crypto because law enforcement and other agencies want to be the first to be able to do these kind of things. So anything that you're signing now, say onto blockchain, might be cracked within 5 or 10 years, so you've got to understand the risk. So the main methods that they are, and they tend to be quite complicated, complex, such as lattice cryptography that IBM implement. There is the good old telecoms error connecting codes, the kind of things that you would see on a CD-ROM for connecting bits. They're coming back again, Hamming codes and so on. There is the multivariate polynomial cryptography, which is really difficult to understand some of the methods. And then there's the good old Merkle trees for hash signatures. So we might see a change in the way that we sign things, and it's likely that we'll sign things with hash signatures rather than using public key encryption methods in the future. So if you click on these links, it should take you to some examples. I've got lots of examples on the website that should work, but few people really understand in depth all these methods. But obviously, if you're interested in this area, then it's a good area to get into. There should be lots of code around. The code tends to be very big and quite complex and might not run that well. So it's quite a difficult area, but quite a challenging area. The area that's definitely happening just now, and we see a lot of the banks moving towards a tokenization infrastructure. So if you remember what we have with our blockchain is that that's a traditional model there of sending a transaction in a blockchain method. We take our private key, we find Alice's public ID, we sign a transaction with a private key, and we put the public key onto the signature. The values of R and S are the two values for the signature, and they prove our public key. They prove that we have the private key for the public key that signed it. So there's a bit of magic that goes on, that we don't need PKI anymore, and we don't need VeriSign to distribute our public key. Because of the magic of the elliptic curve signing, we can put our signature onto the transaction, and instantly people know that we have signed that correctly with our private key. So Liechtenstein is one of the first countries of the world to actually start to articulate this type of method in a legal form, and they created the Blockchain Act. And it was really to make sure that they could create real-world applications around blockchain and crypto signing with some sort of legal certainty. And we have three main tokens that we issue. Payment token, of course, that's the Bitcoin, Monero, and so on. That's traditional cryptocurrency. We have utility tokens where we can have bus travel and we can maybe share the token across different bus companies and so on. We buy a certain number of tokens and then we can just spend them. But the one that's really interesting is the security tokens. Is it possible for us to create a digital artifact and to own something and prove that we own it with a security token, and then to trade those security tokens to pass them on to someone else? So when we buy a house, just now we sign a deed and we give the deed to our solicitor. Is it possible in the future, when the house has been designed and built and so on, to actually create a security token that we can own and then pass on? So the Blockchain Act looks at the transfer of those tokens and provides some legal certainty in the same way that we transfer documents and sign them with wet signatures, what it means to own a token, and then what it means to be in possession of each of these tokens. And then we obviously need to define a custodian, because we're not always going to have a copy of our security tokens, so we might give them to a trusted solicitor and a custodian. So in that way, we can actually give them the private key, or for them to have some way to regenerate the key. So just in case we lose something, then the custodian can take over it. And increasingly, we'll see things like wills written in some sort of form that allows us to be able to pass our security tokens over. This is what it looks like. It's in German. That's why we have this VE tag here. But when you look at it, it's just really, it articulates the law around trading tokens in a way that we would normally enact with our traditional finance model. So obviously what we have is to be able to trade within audit compliance regimes. So typical ones are PCI and Sarbanes-Oxley's, but now we might see something like a blockchain act coming in across the world, and different countries will start to regulate cryptocurrency and tax and so on. In the UK, we have the HMRC, who have rules around cryptocurrency and personal gain. So we'll see that more happening with inside business taxes. Okay, so one way the traditional way that we hide data is we might have a surrogate table, and the surrogate table takes our real ID, and then we create a table somewhere which maps that to a surrogate ID, and then people will only see the surrogate ID. Unfortunately, it's usually fairly easy to map that back to the ID, especially if that surrogate ID is used many times, or somebody knows what the mapping actually is. You can often take data sets together and merge them and reveal data. So there's been many examples. The Netflix database was one where they released anonymized data, and then someone else took another data set, and they could match virtually all of the individuals involved in these things. Another one is the Oyster card in London. I think they've refused to release the data set. They say they anonymize down to a kind of MAC level, but actually you'll probably find if you know where somebody was at a certain time, you could probably trace them through the whole of the network and start to identify people and their phone. So in the tokenization world, what we have is that we trade with tokens, and these tokens don't really have any value to themselves, but we trade them in for our fiat currency. So this becomes high security, and then when we deal with tokens, then it's very low security. So we might see a world where we put all our personally sensitive information behind firewalls and make sure it's all secure. And then out here we deal with anonymized tokens, which then can be referred back to the actual original data. So tokenization infrastructure is to take tokens that can't be cracked, have no side channels or direct attacks, feed them into a data processing infrastructure, send them off with a query to our tokenization service, and then get a reply back. And here, the actual core information within the token, which is sensitive, is never revealed at all. So this is Visa's best practice for tokenization. We have a tokenization server, which has 24/7 monitoring, strong network segmentation, and so on. We generate the tokens. They can be a one-time use, or they could be multiple times. We then have a key management system to make sure that we can recover the encryption keys and things like that. For the tokens, a token mapping to map the token back to original data. And then we have things like the credit card vault, which is obviously have strong PCI compliance. We use good quality encryption all the time. Obviously, the ECC and the RSA might be under threat with quantum computers, but that's what a strong tokenization infrastructure looks like. So there's an example. Bob asked the tokenization service for a token which hides his CVV number. He could hide his bank details and so on. There's an ID on the token. he goes to buy something. The merchant is tricked into thinking that this looks like a valid Visa card number and this is a valid CVV, but it isn't. That gets passed on to the bank, and then they go to the tokenization server and ask if Bob has enough money to pay for the goods, and it says yes, and then it goes ahead and he buys it. Good thing here is the tokenization server also sends back an acknowledgement to Bob to say that it's went ahead, or if it's not went ahead, and probably the reason why. Okay, so I've got an example if you want to click on the PDF there. An interesting area is what's called format preserving encryption. In this case, we can actually make our encryption look like it's actual valid data. So we can take a credit card, we can create a random nonce to be able to encrypt, or a passphrase, and it comes out as a value that looks like a credit card number. In this way, we can trick the infrastructure into thinking that Bobby has put in his credit card details, but it's not. And then it's only when we decrypt these values do we get it back to what the original card number is. So that's called frequency preserving encryption. If you're interested in it, there's a little demo that I've got there that actually shows this working. Please say if anybody has any questions at any time. Anybody? No? Good. So an extremely interesting area is what's called zero knowledge proof. So too often we give away our passwords and all our sensitive information, and really what we want to do is to just prove that we know something. So this is a standard way of describing zero knowledge proof. We have Victor, the verifier, and Peggy, the prover. So Victor looks away and asks Peggy to go into the maze. She must prove that she knows the secret passphrase to open the door between the tunnels, and she must prove that to Victor. So she goes in. Let's say she goes to A. Victor then says appear through A, and Peggy appears through A. She's not proven that she knows the password yet, but she had a 50% chance of getting that right. Again, she'll do the same thing, and Victor comes back and asks her to appear through B. If she's chosen the wrong way, then she can't get through there, so she won't be able to return back. And now Victor has proven that she doesn't know the passphrase. If she does appear, then Victor is more certain that she actually knows what the secret phrase is. It comes from Alibaba and the Secret of the Thieves, where they used Open Sesame to open the cave. And it was this guy here, Odi Shamir, who came up with a method that made this work using discrete logarithms, as we've seen. In a traditional method, what we have is that we pass a hash version of our password, or we store a hash version along with the salt. As we've seen, we now get tera hashes per second. The salt isn't a problem anymore because the salt is stored beside the hash value. We just stick it into hashcat. Everybody uses an uppercase letter, one uppercase at the start and numbers at the end. It significantly reduces the strength of the hashed value. So 10, 12 character passwords are really quite easy to crack these days, even with salt. So we add in bcrypt and we add in PBK DFS2 to make it more difficult, but that kind of just slows it down. It's still possible to crack weak passwords. So the method that we use with zero knowledge is that we create a registration value between Peggy and Victor. We make that a strong registration. Then Victor sends a challenge to Peggy. Peggy does a computation and sends back the answer to the challenge. So it's really a puzzle that Victor sends. If she knows a secret, it's easy for her to to solve the puzzle, but if she doesn't, then it's computationally too difficult to actually do that. So the method that he created is this one here. This is the password that we're trying to hide. We take a hash of it and create a value x. We agree on the value of g and prime number 2. We pass that value as the registration. Peggy selects a v value, sends it over. Victor sends a challenge. She does a very simple calculation, sends it back, and then Victor can prove that she still knows her secret. This is the method that people refer to now. Non-interactive random oracle access is the core of online trusted voting and many other systems now. So we can see here it uses the discrete log methods that we've came across before. They're quite efficient in computation, and it should be able to run these things in the browser. And in this way, we can Bob and Alice agree on this G value and the P value, and then we can pass values back and forward and to prove that that Bob still knows his secret. Whenever Bob loses his password, all he has to do is a reset and then a registration process again, typically with an out-of-band method, and all that's stored on the system is a nonce. And if a hacker gets in and looks at the value, there is no way that they can actually determine what Bob's password is unless they have a quantum computer, which isn't going to happen anytime soon. So there's some interesting methods that are proposed for this, and you can have a look at the website for some examples. So the other area that's happening, will hopefully happening soon, is homomorphic encryption. So companies like IBM with their Z series are looking to implement large-scale computation machines that will operate on encrypted values. So that will start to protect the data as it's in memory, because when we're in memory, we can see everything. So we're doing some work just now about looking at memory that's involved in SSL communications, and we can actually see the keys being generated and the salt value from there. So the memory is the one place that we're not protecting enough, and developers don't spend much time in making sure that the data that they store in memory of the running program can't be interrogated, or with things like a warm boot to be able to go back into the memory and see if there's keys still in there. So basically, homomorphic encryption is to be able to encrypt our values and then perform some mathematical operation, such as an add value here. And when we decrypt, we should be able to find the addition between those two values. So in this way, we could do things like spreadsheets. We could have encrypted cells, and we could still do our computations from there. So with that, we can find out things like who's older, between Bob and Alice and so on, what their total income is, without actually revealing how much income each of Bob and Alice actually have. So as I outlined a little bit earlier, this is the method, the DGHV method, created by Gentry, which is the first full homomorphic encryption. Basically takes our values, adds a secret key, goes into a function, and then gets our value back, and then we can decrypt it as a result. And so this is what it does. It breaks the numbers into bits, and then these become cipher bits, and we put it into a circuit, cipher circuit, and when we look in here, we can't determine anything to do with the original data. This all just looks scrambled and random. But then when we decipher, we'll get the result back. So the problem with this is that we've got to recreate all our functions again, like add and multiply and divide and even simple things. But that's possible because most of what we do is maybe just simple operations of add, subtract, multiply and divide. So as you've seen earlier, if you want to have a look at the demo, that's how it happens. We've got a few random numbers in there, and then that's the message bit, and all we do is decipher. We take our private key and we mod it with the cipher, and then we take mod 2, gives us our bit back again, and we put all the bits back in place to get our result. The other area that's happening, and there's no way that I would ever expect you to understand what goes on underneath, and very few people on the internet do understand this area, is ZK snarks. So ZK snarks, we use methods of hiding data, but still to be able to operate on it. So Zcash uses this, the zero knowledge proof method. The problem that we have is that the traditional methods take a long time to generate the original zero knowledge proof that we're going to use for the puzzle. But that's coming down massively with new methods being discovered. And what it basically does is it makes sure that that very simple thing, that Bob has enough cryptocurrency in his account at the current time to pay for something. You need to mine across all the blocks to find out how much he's received and how much he's spent, and then find out that he has enough. That can be done through homomorphic additive encryption, where you could look at each of the values and you cannot tell how much he's spent, but you can tell if he has enough cryptocurrency to pay Alice. ZK Snarks is really complicated if you look at it, but it has a really smart method of also being able to do the smart contracts. The smart contracts cannot tell the data that they're operating on, so they're pretty dumb. They take the data, but they have no idea what that data is itself, but they can still compute the values, and that keeps privacy within the smart contract. If you're interested, some of the methods are on the website, but they are fairly complex. An interesting development is this Hawk framework that's not actually out yet, I don't think, and this allows smart contracts to run off the blockchain and still be trusted from there, and that would take a lot of computation resource off the blockchain and create an even larger distributed model. The last area that we covered, and I appreciate there's a lot in here, is range proofs and Peterson commitments. So this is where we were with our elliptic curve method. There's the private key. We take G and then we add it so many times, and then we generate the P point, the public key point there. That's that point in the elliptic curve. So a method that's proposed for hiding Bitcoin transactions and other things is what's called a Peterson commitment. Peterson commitment is having a blinding factor, and you cannot determine the value that you've committed to until you release that blinding factor. So I could make a commitment, say, on who is going to win the next election in the UK. I could commit it to the blockchain now. I would apply my blinding factor, and then when we came to the election and then one party won, I could then show you my blending factor and show that I committed to that prediction at the given time. And we can define that because I've put it onto the blockchain. It's well defined when I made that commitment, and all I have to do is to store in my wallet our blending factor. Obviously, if I lose that, then it's never going to be able to be recovered. But it's up to me to be able to recover that if I want. So this blinding factor V is added to it as another point on another elliptic curve. So Mimblewimble was posted in 2016 on a GitHub, and it uses this Peterson commitment method to be able to hide Bitcoin transactions and other things. So basically what happens, we take our blending factor, we take 4 Bitcoins, and then we take, as we saw before, we commit that value here for our purchase, but then we would add in the blending factor, and it's impossible for somebody to see what the value is that we've actually committed to for the transaction until we give the blending factor, we reveal the blending factor. But the good thing with this is that we can transact across the blockchain and still find out if Bob has enough funds to pay for things. The other thing that's happening just now is what's called a range proof, because often we give away things like our age, our income, and so on, where most of the time what we have to do is to prove that we have something in a certain range. Do we have a salary between 20 and 100k? That's the proof that we need, not the specific value. So with a range proof, we go to a trusted entity that Victor trusts, and they have a public key that we can verify. They sign something with a private key and give it to Peggy, and then Peggy can actually give some sort of range proof to Victor to prove that something is within a certain range. So these are this is the paper that came out recently, and it's quite a major advancement within blockchain and cryptography. It's called bullet proofs, and they create very short proofs around these ranges, and also these proofs can be merged together. So multiple proofs can be merged together into a single signature. And it tries to take this problem where we can find out if Bob has enough unspent transaction outputs to buy something, in this case for 2 bitcoins. In a bulletproof world, everything is anonymized, and even the transaction value is anonymized, but we can still process them and find out that he has enough in a certain range. So does Bob have between 2 and 10 bitcoins in his account? We can use a bulletproof to prove that, and we would allow the transaction to go ahead with that bulletproof signature. So Monero implemented it. Monero has implemented many anonymization methods, which has the downside that many criminal gangs are now using Monero rather than Bitcoin, because Bitcoin can be traced. So there is a downside, but at least they're anonymizing the transactions onto the blockchain. So in this way we can prove a range for things. So it's been implemented. We get the aggregation of range proofs together into a single entity. There's no need for PKI anymore for a trust infrastructure, and we can trust everything that's signed with these bullet proofs. And we could do things like prove that a bank has £1 billion of liquidity at a given time. So if an auditor went in and says prove that you have £1 billion of extra cash, through a bulletproof we can actually prove these things. So that was our presentation for this week. Does anybody have any questions?
Yeah, Bill, I have a question about lightweight crypto.
Mm-hmm.
So where the encryption happens, is it so you mentioned RFID. So the RFID tag is not gonna be encrypted, correct?
No, yeah. So I'll just show you the LA method. Just trying to find. Yeah, it's a problem to find the ID of a device. Let me see if I can find LA. So LA is a asymmetric method, and so the RFID tag has a stored private key of E here, so that's embedded into the tag itself. It's unique, and then we generate the public key, which is E times P. So it's using an elliptic curve here. That's the public key. So then it's a bit like the elliptic curve Diffie-Hellman method. So then the reader creates its own private key, sends over that. And we've got this point as A, Then we take the A value and multiply it by the private key. We get C back. We send C back and B back, and we can compute B times lambda, and we should get the same value from there. So this code here, I think, implements it. So I'm using this curve here. If you want to try that.
So is your RFID generating the public key?
The RFID tag has a private key built into it.
Yeah.
It can then, it knows P between the two of them, so it can also have a burned-in P if it doesn't have to compute that each time. So it can have both this E and P value. Obviously, this would be protected, so you couldn't view that, but you could view this B value, and then this one generates this new key pair.
So what is the advantage of doing that?
So I can prove that this is this RFID tag. No other RFID tag will have that ID. This is unique. So I have a whole list of ID tags that I have for my devices. I send it a challenge, and then what it comes back with, I check this C and D value, and I can prove that private key is really that tag, because it's not possible to be able to fake that value. It's a challenging area, and if you do find out the private key, and you might do an X-ray of the device and see the key, but in this way we can at least have an identifier for the tag, and every time we see the tag we can identify it as that specific tag.
Well, what I thought, we can actually copy that tag, because at the moment you can let's say if you have a card, you can write on that card the same value. So what's the point of encrypting it when
you would have to burn it in and make it read only, so that it couldn't actually be seen and it can't be interrogated. So you can't tell it from the values that come back for the public key or from C. So it's impossible to find out by listening to the tag what its private key is. So that would be read-only key, and you can't modify it. If you did discover it, then you could obviously reprogram another device with that, but hopefully you can keep that secret.
Okay, thank you.
Okay, does anybody have any other questions? Good. Okay, so let me have a look at the coursework. Got time? Yeah. Okay, so I remind you all to have a look at the areas that are defined, to try and find some research around these areas, and to find something that interests you, and hopefully go and find a GitHub and download some code, see if you can get it to run, try some test vectors, and then to try and to give it some sort of evaluation from there. So remember that we have another 2 weeks of teaching, and then 2 weeks of the Easter break, and then we're back for a full week. And then the week of that, the week 14 of the Friday, is when we get our second test, Okay, so we've got 1, 2, 3, 4, 5 weeks, more than 5 weeks to go before the test. Then the coursework is the week after it, and then you take the Monday of the next week of week 16, and that will be the coursework hand-in date. So just make sure that you optimize your time. You've got 30% for the next test, and then 40% for the coursework. So you don't want to go down in one and then do extremely well in the other one. Just kind of balance the two together. So I'll release a study guide quite soon that you can have to read over the Easter break, and obviously you can go into the Slack space and ask questions there. Hopefully you're up to speed now with the way the tests are conducted, open book test, and you kind of know that the level of questions and the time commitment can be a bit difficult. Does anybody have any questions? No? Can somebody say hello, just in case I've lost?
Hello, Bill. No questions.
Good. Yes, I did lose. There was 1 week that people were saying things and I couldn't hear them, but I'm glad you're all still there. And I know it's late in the evening, and I appreciate all your effort in coming on the call and all the great questions that you ask. And hopefully you're all coasting to the end of the module now, and you can have a rest after that. Does anybody have any final questions? No. Well, we'll have another session next week. I'll try and get some more information to you. Hopefully the lecture will get recorded this week. And thanks for all your hard work. And I look forward to speaking to you next week. Okay?
Thank you.
Yeah,
thank you, Bill. Take care, everybody.
Have a nice evening.
Bye.
Yeah, thank you. Bye-bye.
You too.